Hi, I'm Alden Hart, and this is Rob Giseburt. We're here with Synthetos. Our other partner, Riley Porter, will be at Maker Faire. He's not with us today. We're here to talk. We specialize in motion control, and as Zach mentioned, we provide electronics for the Shape Oko. And let's see. What we're here to talk about is some of the evolution that we've come across to how do we take what is actually a fairly complex domain and turn it into something that's more accessible so that we can build more interesting products and really move into the industrial space, move into process control and other things that are quite difficult. So here's an example of one of the things. This is a speed test we did on an Ultimaker. So
we were supposed to have
don't
audio.
really have audio, but it's making a lot of noise. There we go. Yeah. So that's an example. We'll have that on display at Maker Faire along with a bunch of Shape Okos. Thank you. So what I'd like to look at is where are we from a maker perspective with motion control? Where are we in industry? What's the gap? How do we get there? So if we take a look at motion in a single domain and system integration. So motion in a single domain, as a maker community, we've done most of this, not really all of it. We've got good path planning. We don't really have optimal path planning. If we want to get to the actual industrial level, we've got to get pulse integrity, motion profiles. If you're doing a high throughput screening, drug discovery type of thing, and you got a drop on your pipette, and you're moving real fast, you don't want to move too fast, but then when you go back and you don't have it, it's a different motion altogether. And then these various other things that we need to get to. So the gap between where we are in single domain motion, say just moving in XYZ, or just doing a single PNP, a single 3D printer, let's say, isn't that great. But when you get to the next level, we have a long way to go. We don't really have a good way, a common way of doing device integration. Everybody's doing their own stuff. Complex machinery has multiple motion domains. A complex PNP will have 6 things going all at once. They're coordinated. They don't crash into each other. We're really nowhere near that from a community perspective. They do optimal job planning. What happens when something goes wrong? Can you handle an exception? Can you do that without dropping the line and putting hours into your production schedule? And collision avoidance is good unless you're doing robots, boxing robots, and then maybe it's not so good. But those are the kinds of things. So how do we simplify this domain? We need to be accessible, and these are our 4 sort of major audiences for this. The Arduino level user, web programming, a machinist or other domain expert that doesn't really want to program. And then, of course, we don't want the tools to get, we want to make them simple, but we don't want to lose precision. So that for professional uses, we want to be able to use the same tools. Components, of course, are nice, and we've got this beautiful ecosystem of Arduino shields and things of that. But what's interesting is how do we find a simple way to package things that aren't already in that ecosystem? How do we arbitrarily extend the ecosystem to things that we can find? So the tools we're going to talk about, some of the things that we've come up with, we did this because we had to for our domain, but we're looking at how do we move, how is this generally applicable in other domains? So Rob will talk about Motate, which is a hardware abstraction layer. Kinnan is a set of standards. It's not really standards, they're conventions for how do you put a number of these things together. And really this is all aimed at how do we get to a hardware mashup? How do we treat hardware just like REST on the web and be able to say, I need one of those, push them together, I've got a user interface for it. How do we get to that point? So I'll hand it over to Rob. He'll talk about Motate.
Thank you. Motate is sort of the glue that binds all of this logic about motion planning and all that to the actual hardware itself. And the intent of this is that it's sort of a methodology of programming as well as an API. And the intent being that It's easy enough for beginners to learn how to program on, powerful enough for the pros to put it into a professional end-user product. And, of course, hopefully making beginners into pros. And,
You got it.
back up. One of these buttons makes this thing work. All right. So on the beginner programmer side, we could just say Motate is like an easy-to-learn embedded language. Again, speaking to beginners, don't know how. Warning, code. I'm going to put code up. I'll skim over it because there's very little to it. If I say, in English, I want to turn pin 13 on and off, here's the code to do it. You create a pin object and you set it to 1 to high and set it to 0 to low. Read the pin. I want to read the level of pin 12. That's what you say in English. In Motate, you would just create a button pin and then put that in a statement. It reads that pin when it gets to it, and then you can do something based on that result. Timers. I've seen very large blog posts about how to do timers on microcontrollers. It was a very difficult task trying to simplify this. Believe it or not, that chunk of code is an extremely simplified version of setting up a timer. And I'll look at that a little bit more. On the left, I have the Motate code. On the right, I have the raw code if I wanted to program the exact same thing, right and left, for the ARM that's on the Arduino Due. Now you see this massive pile of acronyms that even after you know what they mean, you still have to look them back up again 2 weeks later when you go to read it again. And I'm not going to really try to explain what they all do because I forgot. But here you can see, this chunk lines up to that one line in the Motate does that exact chunk. That line, or that chunk there, is handled by that line in Motate code. The font messed up on this when it translated, so they're a little bit off. But TC start over there on the right lines up with my timer start over here on the left function. And then you actually do something every 1/50,000th of a second in this little do something chunk right here. Same thing over there. Like I said, equally functional. Actually, the Motate code compiles down to smaller, requires less space, using the atmel libsam hardware abstraction layer on the right. So the real power comes in. Again, the alignment goofed up a little bit, but if we want to change what timer we use, on the Motate code we have this one define up here. Timer 3. We change that 3 to a 4 or a 8. We have 8 timers on this particular chip. If we want to change that, that same thing to any other timer, here's all the places we have to change the code on the right. Again, the alignment's a little bit off, but you can count. So, and that's just to say that particular chip. So what if we want to talk about, what if we wanted to put the same code on the AVR? Well, the hardware abstraction layer of Motate, we can potentially put it on any of those processors. We don't have ports for all of those now, and the ones that we're still porting to some of those, but ATmega, ATX Mega, and Atmel ARM are definitely up front. So, got 5-minute warning. So, for those that know professional programmers, there's already a lot of value there in what I just said. So I'll skim over this. Basically, I am using C++, and I know I'll get flack for that, but it's optimized C++. I'm a software engineer by day. I know what to avoid, and this avoids it. It's designed with good UI design principles, because an API is a UI. I know a lot of people don't believe it. And we don't compromise performance or usability. Use Mirage interfaces, opaque interfaces that are designed for the compiler so that it boils away during compiling and optimizing. So that when I say LED pin equals 1, on the AVR that compiles to 1 instruction and that executes in 2 cycles. On the ARM ARM that's on the DUE, that compiles down to 2 or 3 instructions and executes in 2 to 5 cycles. That's the absolute minimum time it takes for those processors to perform those functions.
So the second thing we found is moving towards hardware mashups. So we're defining a hardware mashup as any set of hardware that's dissimilar but needs to work together and is controlled in a single unit. We're doing this as RESTful hardware. What is REST? REST is a set of resources which are things, representations of those, which are things like a line of JSON. State transfer, can you get the state from it? Can you set the state? And then when you take a look at complex systems like, say, a 3D printer, there are many different things, like a three-dimensional domain, an extruder component, some heaters, and maybe a camera or something of that sort. It's useful to recognize that REST is not HTTP and HTTP is not REST. REST is just an architectural style. It's a way of programming. And you use these basic concepts to simplify how you deal with things that are actually fairly complex at the endpoint. We run REST over USB, SPI, RS-485, and of course HTTP as well. What is JSON? Why do we use it? JSON is JavaScript object notation, which is a fairly concise way of putting a bunch of data on a single line or in a single structure. It's much more concise than, say, XML. It's not as concise as raw binary, but it gives you a lot more flexibility. And it's already in almost every compiler, every language that you're going to use. It's in JavaScript, of course, but Node.js, Java, Python, Ruby, pretty much anything you're going to do. And what we think is important is that we put this on the device itself. We don't front it with a gateway. We actually have these running on those processors, on the ARM, XMega, and the 328 that's running on the Arduino Unos and all the various variants of that. Kinnan is a project we defined separately from Synthetos. We wanted to distance it and just make it more unowned, if you will. And that's where we're defining the protocol, we're defining the protocol and the conventions and then the hardware compatibility. So what can you do with JSON? The top one's a line of JSON. That's a command that moves G code to X20. You can configure motor 2 with that line. All the things that you would use to configure the motor are on that line. You can get a status report. Where is it? How fast is it moving? You can filter the status report so that you don't have to get everything back all at once. And you can do addressing. Address this to the master. Master's motor number 2 is going to take this. This is very similar to the pub sub stuff that Pinocchio is talking about. Do the same thing for the slave board. You're running all these boards in parallel.
When using multiple controllers at the same time.
Yeah. So you can build networks of these things and use JSON, its inherent namespace, as a way to do the addressing. We use a subset. We dumb it down. We use a subset of JSON. We only use these components of it. We don't use dynamic memory allocation. Oops. And just so you know, it's not as bad as you think, efficiency-wise. These are some comparisons. Basically, that component, the flash footprint, which does the parser, the serializer, a dispatcher, and all the floating point lives, adds about 4 to 6K into an Uno. And we use a bit more space on the bigger chips. The floating point marshalling is manageable. It's not. You're not going to wait forever to get these kinds of things in and out of your system. So please visit us. Look at Kinnan. Look at the Synthetos GitHubs. If you're going to look at the GitHubs, go to the lower branches, because that's where all the work is going on. And we're happy to answer questions. We'd love to have people collaborate and understand how to use these techniques for your projects.